Why did spark gaps lead to modern continuous wave modulation? Imagine the earliest days of wireless communication, where sparks flying in the air were the main way to send signals. That's how radio transmission started. Spark gaps were the first tools used to generate radio frequency signals. They worked by quickly discharging a capacitor through an air gap, creating brief bursts of oscillating current in an LC circuit connected to an antenna. These bursts produced damped waves, which are signals that fade out quickly and contain many different frequencies. Because of this, the signals were noisy and not very efficient. They also had a broad spectral bandwidth, meaning they spread across many frequencies, causing interference with other signals. This made it hard to send clear messages over long distances. The limitations of spark gap transmitters made engineers look for better ways. Spark gaps naturally produced interrupted, damped waves instead of steady, continuous signals. To improve this, inventors developed quench spark gaps. These could extinguish the spark at just the right moment, allowing the LC circuit to ring freely at a single frequency for longer. This created longer-lasting, less damped oscillations with a narrower bandwidth and a purer tone. These signals started to resemble what we call continuous wave transmission. They were more stable and easier to modulate for different types of signals. From an electrical engineering point of view, the shift from spark gap damped waves to continuous wave modulation was driven by the need to reduce interference and increase range. Spark gaps emitted signals that covered many frequencies, which caused interference with other transmissions. Continuous wave signals are narrowband, meaning they stay within a small range of frequencies, making them cleaner and easier to work with. They also allowed for more reliable detection and demodulation, especially for Morse code and voice signals. This stability opened the door for more advanced modulation techniques like amplitude, frequency, and phase modulation, which are the foundation of modern analog signal processing and control systems. The transition involved several key steps. First, the development of quench spark gaps that quickly extinguished sparks, letting the LC circuit oscillate freely. Then, rotary spark gaps increased the rate of spark repetition, improving signal quality. Eventually, spark gap transmitters were replaced by vacuum tube oscillators. These could generate true continuous waves that could be modulated smoothly rather than in pulses. This evolution was essential for creating the stable carrier signals used in today's communication systems. So, spark gaps played a vital role in early radio technology, demonstrating wireless transmission. Their physical limitations led to innovations that produced cleaner, more stable signals, paving the way for the continuous wave modulation techniques we relying on now.